traveling at nearly the speed of light, they actually contract in length. This is known as length contraction. So you might be thinking, yeah, cool, I mean, that makes sense. If an object is moving by really fast, my eyes don't have time to keep up with it, so it looks shorter than what it is. But it doesn't just look shorter, it actually is shorter. If you fire a meter-long missile at close to the speed of light and take a snapshot of it in mid-flight, it will actually measure to be less than 1 meter. By how much depends on how fast it's going. So if Alberta is running toward the barn at near light speed, from your reference frame she contracts in length in the direction of travel. In other words, to you, she looks all squished up. So it's perfectly plausible that both doors can be closed with her inside, even if it's just for a split second.
Now imagine just the slight possibility that we need to view basically things relative, like there's different dimensions acting out, okay? And the dimensions would be probably best described as like different viscosities of time. Okay, so you have a fluid that we're typically in right now, and it's of a certain viscosity, which means time is moving at a certain rate within that. Now, the quantum level would be an accelerated form of that, in which, if you imagined there, time can exist in more than one place at that moment, okay? However, there's another one in which you can go the speed of light, and you're going into a separate dimension in which isn't as contracted, okay? So, if you're in water and there's a boat, if it's moving at a certain level of speed, it's displacing this much in that underwater, okay? If you're looking at it from this perspective, you're swimming underneath the boat. The faster you move that boat, the more it goes up into the other dimension. Thus, the more squished from our perspective it becomes, because relative to us, that's what we're seeing. So it's moving faster, however, its mass is actually going more into another dimension, similar to being like the difference between like air and water.
While this is all very bizarre, it still isn't a paradox until we consider things from Alberta's perspective. And why would her perspective be different from yours, I hear you ask? Well, because all motion is relative. Imagine you're at the train station watching a train go by. From your reference frame, you are standing stationary on the platform and it's the train that's whizzing past. Now imagine you're on that train. Now you are standing stationary on the train and it's the platform that's whizzing past. So you might be thinking, well, really it's the train that's moving, even if it doesn't seem that way. But think about this. Imagine you're floating up in space watching the train drive across the Earth. It's a very high-speed train, traveling at 1,000 miles an hour east to west. The Earth spins on its axis 1,000 miles an hour in the exact opposite direction. So to you up in space, it looks like the train is stationary and the Earth is moving. All motion is relative. Now let's get back to the barn. So far you're an observer watching a squished up Alberta run through the barn. The timer goes off, closing both doors with Alberta inside.
Meanwhile, what happens if sometimes motion affects your placement within a dimension? And the dimensions we're talking about are like stacked on each other, in which we are existing in a singular dimension that other things are also traveling through. Okay, so our dimension is of this basic fluid viscosity. However, another dimension that's interacting with it is at a separate viscosity. So the difference between like water and the atmosphere is technically, you could argue, all space is kind of acting out like a fluid, okay? Whether if that seems nonsensical or not. But when you dive into it, it's not. However, if we're in water once again, and we're looking at a boat, the faster it goes, the more it actually starts going up. It's raised more. Its mass is raised more because of motion into a separate dimension. Now, none of us are really traveling typically at any of these speeds to even begin to comprehend this. However, this would then argue you could travel faster than the speed of light if you figured out a way to go fully into that dimension. However, to an observer, you would probably be squished up and look like a particle of light, or similar to it, if you were able to figure this out. So the argument, and this would also argue against, within this viscosity, we have a speed limit. There's only so much fast we can go. However, that still doesn't mean that if you can view this, and if you can argue and prove that there's a separate dimension that you can actually like pretty much go up into in this way, you might have to create a special spaceship that's specially designed to completely encode the outer thing so that you could actually raise up into it and then like zoom across. I mean, these are the like concept of like space movies and whatnot. Like Star Trek kind of has this concept. But if you're viewing it the same way you would as a different viscosity, it's more easy to understand this. Einstein is not squished up. Einstein is moving at a speed that takes most of, or half of, or whatever percentage of his mass into a separate dimension, so that the barn, which is probably confusing most people, is no longer affected. But it's easier to view this more as a boat in water, and I'm a fish or whatever, or I'm just someone chilling out underwater, and I'm looking at this huge boat. And the faster it moves, the more its mass actually raises up. So the fact that it gets squished up from my perspective is because relative to me, that's my perception of what's going on. However, what's really going on is more of that boat's mass is actually in a different dimension from the water to the air dimension. View it similar to that.
They open again and she continues on at near light speed. The real paradox begins when we take a look from Alberta's reference frame, because to her, she's stationary and it's the barn that's moving toward her at nearly the speed of light. So then if the barn is what's moving, it's also what's getting squished up in length contraction, so there's no way that at any point Alberta could fit in the barn with both doors closed. So from your reference frame, Alberta easily fits in the barn, but from hers, it's impossible. So what's actually happening? I mean, surely you're not both right. Well, actually, you are. This is the juicy part. The solution lies in what we mean by the doors closing at the same time. Special relativity tells us that there is no absolute time. There are only reference frames. We experience different things happening at
Which would make sense if time is multidimensional and acting out vastly different. So, like in the quantum world, time is excessively sped up. That's why particles can be in two places at once. Because that viscosity has time much more fluid, versus our reality where it would be thicker.
different times depending on where we are and how fast we're moving. The reason that you haven't experienced this and why you might not believe me is because these effects are only obvious at near light speeds. The fastest you've probably ever travelled was on an airplane, which are about a millionth of the speed of light. Relativistic effects are pretty hard to detect when you're moving around so slowly. So if we look back at what's happening with Alberta and her pole, from your reference frame, the timer goes off and the signal reaches doors A and B at the exact same time, and so both doors shut simultaneously with Alberta safely inside. Now from Alberta's reference frames, the barn and its doors are all moving. Door A is effectively running away from the signal, so it takes a longer time to reach it because it has more distance to cover in the chase. Door B, on the other hand, is moving to meet the signal, so it takes a shorter time to reach it because it has less distance to cover. So put together, as Alberta enters the squished up barn, door B closes and quickly opens again, letting her through. And then once the back of her pole is inside, door A closes and opens again. Told you it was juicy. Thanks so much for watching, guys. I hope you enjoyed this video. If you did...
But you could also argue things appear squished up because its mass is no longer playing out, because relative to our time, it is no longer playing out in this viscosity that we experience, you and I. And the best way to try to visualize this would be thinking about how this would work. And so, if you have something moving, at a rate in which the faster you go, the more mass it seems to have, less of, right? You're transferring it. This would also be able to explain certain particles that seem to be massless, because they don't necessarily have to be within our dimension of space. We might be seeing them, but it might be just like being able to view up and notice something that does have some effect in the water. However, it could just be like something motioning just above the surface of our thing, and we still kind of have hints of it, but very few things within our dimension are actually affected by it, because it's pretty much playing out at a different viscosity than what we are experiencing. Which is anyway, that's probably, I would have to probably find a different way of arguing that aspect of it. Anyways, take care. God bless.